Hello. My name is, sorry about that. My name is Leonardo Ramirez, and today I'm gonna be explaining my argumentative exam. Let me set my chrono um, so that I don't miss out on time, and let me share my screen. So here we are. Okay, so for the problem number one, we have this circuit right here. It was pretty easy to manipulate it because, well, we just have to consider what are the nodes we have. And, well, here we have the V battery one. Here we set the ground one to 0. So let us go through the nodal equations, which are, well, pretty easy. We are just basically considering the voltage we are analyzing, and then we are subtracting the one who is like kind of connecting with that one through a resistor. So we have all of the nodal equations. And if we then rearrange it into a linear form, we have all this mess. Well, I don't know what else I'm supposed to say about it. I think it's pretty clear that if we now use a matrix form, well, we can see what are the voltages that we are kind of looking for. Let's remember that V1 is equal to the V battery because of well, how the circuit is done. And we also have V9, which is equal to the ground one. And we also have to take into account the current, which is, sorry about that, which is here. So let us go through that real quick. Here I have my code. You can see it in the PDF, of course. And here are the results at each node, which actually match the one from Circuit Lab. So that means our results are close enough. So this is a valid simulation. And here we calculate the voltage drops, which is basically the highest minus the lowest. And we also have the currents, which is taking into account the resistor value. Now let us go through this. This was a mess. This was complicated, honestly. But well, the first thing that I tried to do to approach this type of examples is just rearrange it into a form that we kind of know. And then it's basically the same. We have to kind of evaluate the nodal equations. Here I have them. Yeah, Circuit does not allow to use same legends, so that's why I chose R6. It's equal as R4 just to clear out confusions. And well, as you can see, I tried to do it in the same way we did it in class. We also have the linear form, then the matrix form for both of them. Both here is the other one. Well, yeah, then we did the same thing with MATLAB. We did the same thing with CircuitLab. And here our results differ. I think they're pretty close to the real ones, yet they are not the same. And the discrepancies may come through the way in which I analyzed it. Like maybe I should have considered series or parallel or maybe super nodes. But well, to be honest, I'm not that kind of used to them. So I tried to do it in the simplest way possible. And those were the results. Um, well, yeah, according to me, those are the only nodes existing in there. And yeah, let's say we did everything kind of right, but there was something missing in the initial analysis, let's say. Now, let us go through the exercise number 3. Let's remember that we are trying to do this in the very quickest way so that time is sufficient. So here we are being asked, sorry, what acceleration does it experience due to electric field as it moves 1 centimeter down to the lower plate, what speed and kinetic energy, and how much time. So we can see that this has an approach with kinematics and kinematic formulas and values. So first, it's pretty easy. We just equal the force to the charge and the electric field. And yeah, we can, how can I say it, replace um, kind of, we have to remember that mass times acceleration is the same as force. So then in order to pass it to, well, yeah, charges, of course, um, yeah, we can just put here and replace the force um, in second Newton's law to this one. And then we can continue doing some evaluations and calculations. And then we have to use kinematic formulas. So here we have the one to calculate the final velocity after traveling this, which was the 1 centimeter, I guess. Yeah. And this was our final value just by replacing some values. We have to remember that this is a -1 because, well, it's going downwards according to the problem. And, well, kinetic energy is exactly the same formula we have been using for the whole career. So here we are given the value of mass. We also calculated the one of V previously. So yeah, and in order to calculate the time, well, we also have to take into account the relationship of kinematics, and that would be the final result. Let's remember that since time cannot be negative, well, in this case, it would have not any sense to have it negative. So we are just kind of erasing the minus from the acceleration, which in this case, it's only kind of telling us that it goes down, as the problem suggests. So now problem 4, this one was actually pretty complicated. I don't know why, but well, let's try to give it a try. Yep. So by Pythagoras theorem, we can actually calculate r, which would be the distance from the center to any point. Well, of course, it's kind of a square, so it's easy to approach. And this would be the value of r. Now, let us take into account unit vectors, but for simplicity, I divided them into the x components and the y components. So, yeah, here we are just taking into account that this one is the vector. This one is the magnitude of it, which is this one. So we are actually getting kind of coordinates in a Cartesian system, according to me. So we did that with all of the forces, with all of the, well, yeah, we are kind of evaluating forces at the position 1, 2, 3, and 4 with the different charges. Let me check. Yep, those Qs. They have the same magnitude, so that makes the job quite easier. And well, let us kind of continue going through that. So yeah, if we apply Coulomb's law, we are taking into account this type of Coulomb one. I know there exists the one with where you kind of is not square but cube these are, but this was way easier for me to understand since, well, we have R, which was calculated in the very beginning by the Pythagoras theorem. And then we also have here the two charges, which we are kind of analyzing. And we have here the R. What can we do with this R? I mean, yeah, it would be kind of complicated to simply erase it or trying to simplify it, but let us work through that. Here we're also calculating the separation vectors, but we are considering kind of the exchange of the signs due to, well, what our charges doing, you know? So we are simply changing the how can you say it? Yeah, the final signs of the separation vectors so that we are being indicating if they repel each other or if they attract, which is kind of an essential and crucial part in order to make kind of this analysis. And well, the approach that I tried to do was simply doing it like separately for X and for Y, so that at the end we can kind of add them up in the same formula since they are going to have these same terms, you know, the Coulomb's law. And so that, well, yeah, we are kind of evaluating it as a formula at the very end. So yeah, the R we are taking into account is the one we calculated from the unit vectors. We have here X, here Y, obviously. So let us go through that real quick. Here we have um, the same formula for, yeah, kind of everything because, well, it was very easy for us to simplify it into q squared because of the fact that, well, they have the same magnitude. So we are able to do this. And yeah, so at the very end, we can kind of sum them up since they have the same, yeah, same terms. So here we end up with a 0, and in y, of course, doing the same kind of evaluation with the unit vector, we get a -4. So if we kind of combine these two, we have the final formula for the evaluation of the net force, the total force. What is this minus telling us? It's that the net force has, like, it goes down. Let us say it like that. So yep. And here we have the MATLAB, which is kind of done specifically for this one. But you have to understand me. I'm actually going insane with all of the week 4 and week 5 things we have to do. So this was kind of easy. You can check it out. Of course, I'm going to upload this PDF, but it's basically just the same thing, just in a computational kind of approach. So that at the end with the, I think it was labeled as practical question. Yeah, practical question. Here we have the value for A, which is this one. And well, we also have to take into account the vacuum permittivity value. We have to take into account the charge. And yeah, at the very end, we can see that it kind of matches the analysis with it, with X component being 0 and with the Y component going down with this negative sign. So we can say that it was kind of a success. And for problem 5, first, what we have to do, oh, sorry, it's lagging. What we have to do is just like clear A out of the equation that we solve for A with the values we are being given. Of course, we have to be careful with units as always. And for part 2, it was kind of easy. We did this in class actually. So we are simply kind of replacing this Q max with the percentage which we are trying to look for. So in this case, it's 0.25, 0.15, 0.75. And if we perform all the calculations, we end up with the time in seconds, which was the thing we are looking for, as well as with this charging process. Well, that's important to highlight. First, we're talking about charging processes, then discharging processes. So let us say the procedure is kind of easy, but here we also have the time, which is important in order to evaluate. Then if we want to plot it, well, it's basically just defining a time vector, then calculating Qmax by using the voltage of the battery and the resistance given. And we are using subplots in order to look for the final graphs, which we are going to just show here by means of only one figure and the subplots. This matches the analysis done in class, so I'm very happy and satisfied with the final results. And well, based on the results and plots, why thinking in terms of tau is useful? Well, tau constant is useful because you get the idea directly about how fast or slow the circuit will be. This means by calculating tau, we can directly have an idea of how much time it would take for the capacitor to reach some percentages of the Q max. Like for example, in a sitting class, it takes about 5 tau for the capacitor to be fully charged, or well, we can have an idea of how much time it would take to charge until some specific percentage, as it was asked in the exam, actually. How can we find the constant helpful in predicting sensitive behavior? Well, as I said, if we calculate things and we play a little bit with the values and the constant and everything that this is giving us, we can define that 5 tau is, yeah, what it takes for the capacitor to reach its almost total capacity for charging and also for discharging. So we can kind of predict some things from here. And well, that's it.